Hello again, wildM here. Today we'll be talking about some other symbols that you may want to use in the first round. Sinks, sensors, flip-flops, fusion, fission, and pausing. Let's go ahead and jump right in. Here's another puzzle focusing on efficient transport. Can you see the problem with this solution? Well, with the cyanamide, the quickest way to get it to output omega is to grab it from the bottom, rotate twice, and drop it in the top left corner. However, the sodium nitrate is a different story. For that, you only need to rotate the molecule once before outputting into psi. Since these paths otherwise take the same amount of time to run, the delay from rotation will cause the red Waldo to be one cycle ahead of your circuit and crash. There are three ways to take care of this. The first is to widen the circuits and avoid rotating. Needless to say, that's a terrible idea if you want to be fast. The second way is much better. The synchronize command causes a Waldo to stop. It will only start moving again once the other Waldo hits the sync as well. So what's the third way? Well, I'll show that off later in the tutorial. Oh, and there's also a nifty bug that you can perform with syncs, but I'll let you guys check Google for that. Sensors are the most configurable symbol in SpaceChem. They can be programmed to sense any element in the periodic table, even ones not in your puzzle. When a matching atom overlaps with the sensor symbol, it redirects Waldo traffic in the direction that you specify. Though the most obvious function of a sensor is to split inputs based on molecule, that doesn't tell the whole story. Sensors can also be used to allow a Waldo to traverse a path differently based on what stage of the production process it is in. Let's look at a couple of examples. Here's one of the more obvious uses. If you need to repeat a process that forms a long or circular molecule, a sensor is an excellent tool to let you know when you've reached the right point. Sensors can also be used like sinks. In this example, the red Waldo hugs a wall until it detects that blue has built a sufficiently long chain. Well, those are most of the applications of sensors that I can think of. There's one more thing that I want to talk about before moving on, though. What if we didn't have a sensor? Well, there are a few ways to handle puzzles like that. The easiest way is to exploit the shape of the molecule to your advantage. Here, the red Waldo drops either molecule, only picks up the gerdite, drops and outputs that, then only picks up the siderite. Oh, and you'll notice that the blue Waldo constantly hammers on output psi here. I do that so that my solution will finish one cycle earlier, as the last molecule to be output will always be gerdite, as you'll see later. There are other ways to separate atoms and molecules without using sensors. How could we separate two atoms that have a different color? I'll let you guys figure that one out on your own. I've put a sample puzzle from the last tournament in the description for you to play with. Okay, so let's talk about flip-flops. Let's say we want to do something 3 times before outputting. Maybe we want to create sulfur trioxide, the primary component of acid rain. Well, you could do it with just the symbols from the first tutorial, but it isn't going to be pretty or fast. Flip-flop basics. If you can make a flip-flop for any prime number, 2, 3, 5, 7, etc., you can make a flip-flop for anything. And you can make a flip-flop for a prime number by stringing flip-flops in a series. 1 for a 2-count flip-flop, 2 for a 3-count flip-flop, and so on. In this 5-count flip-flop, it goes up 1, comes down 1, goes up 2, comes down 2, you get the idea. So now we know how to make a 3-count flip-flop. Let's put that to use. That looks much better. Instead of a jumbled mess, we have a nice, clean loop that repeats 3 times. As a side note, you could also do something similar if you had a sensor in this puzzle. Just have the sensor over where the first oxygen would be after 3 rotates, and you're done. For this example, I will consider the bond command here our process. It represents some task that we want to complete. There are 2 main ways of using flip-flops. The first is, as seen before, repeating a task X number of times, then completing your process, then starting over. The second is repeating a task X number of times, then completing the process, then doing nothing. I would call the first one a circuit and the second one an exit. I make this distinction so that I can keep talking about this without being too confusing. With that said, it is much easier to make counters for an exit than for a circuit. Yes, I'm completely aware that I missed a symbol in the top demonstration, but as soon as I saw it, I thought it would make a perfect example of the stupid things you can do in SpaceChem. Anyway, as an exercise, let's say that we want to make a 17 counter. In the case of a circuit, the best way to make a counter is to break it into its prime factors and string those smaller counters in parallel. For example, if we wanted an 8 counter, we could combine 3 2 counters as demonstrated. If we wanted a 10 counter, we could combine a 5 counter and a 2 counter. But we're not doing that, we're making a 17 counter. The prime factors of 17 are 1 and 17. So we'll have to use a whopping 16 flip-flops to get something like this. Well, that's certainly terrible. It uses a ton of symbols, and it takes forever to run. Look at that go, we're still not even done. Let's hope you never need a 17 count circuit. Now let's move on from this atrocity so we can see why a 17 count exit is so easy. To start building an exit counter, start with the circuit for the power of 2 above your number. So for a 5 count exit, you would need an 8 count circuit. For our 17 count exit, we need a 32 count circuit. 2, 4, 8, 16, 32, okay, we're good. From there, all you do is switch the direction of the flip-flops that total the amount you want to subtract from the larger counter, sort of like preloading a number in memory. However, you can only subtract powers of 2, but that isn't too bad. These counters represent 1, which is 2 to the 0th power, 2, 4, 8, and 16. So 17 from 32 is 15, 15 is 8 plus 4 plus 2 plus 1, so we switch our 1st through 4th flip-flops counting from the right. And then we let it run, and it acts like it's on circuit 16 already, so that means it'll go on for exactly 17 times. Ignore this part if you're confused already, and come back to it some other day. Hopefully it'll make sense then. If optimization is your lifeblood, you may have realized that you can save a few cycles by using a 3 count to break out of your production loop, and build the rest of your exit counter with 2 counts. This is because you only deviate from your main path every other circuit, saving on average 1 cycle every go-around. In this example from the last tournament, we have a 24 count circuit that has been switched off on the 6th to work as an 18 count exit. Wow, I just like loops, I guess. One final note on flip-flops. If you run your Waldo into a wall, your flip-flop will be delayed by 1 cycle. This is the 3rd method of getting your Waldos in sync that I mentioned earlier. Well, I can't think of any other flip-flop applications at the moment. Let's talk about fusion and fission. Despite what you would think, this shouldn't take quite as long. Fusion is very easy. As long as you have an atom on the right side, if you hit fuse while something is on the left side, the atomic mass of the two combine and form a new atom on the right side. In this case, 6 and 6 is 12, giving you magnesium. A couple of warnings though, if you fuse in a way that decreases the maximum bond limit just below the number of bonds, those excess bonds will be destroyed, as it did with argon just now. As for which are destroyed, I'm sure there's a way to know which bonds will break if your atom is surrounded by bonds, but I haven't looked into it too much. In any case, you usually won't run into problems with that. In addition, your fusion cannot total more than 109, the heaviest real-world atom in the game. If you attempt it, nothing will happen and your simulation will usually crash if you expected the fuse to work. This quirk can have some applications. Remember when we took advantage of molecule shape earlier? Fission is hard to use in puzzles. It's probably the hardest feature in the game that doesn't involve breaking anything. If an atom is on the left side, the split command will divide the mass into 2 whole numbers and output the smaller half on the right side. So if you have a fluorine, 9, and split, you'll wind up with a boron, 5 on the left, and a beryllium, 4 on the right. This can break bonds just like fusion, so be careful. Know that you can split any and every atom, except for hydrogen. Naturally, you can't split 1 into 2 whole numbers. Splitting while something is occupying the right side, as expected, will crash the simulation. Now that I've told you that, let's talk about the exceptions. If you remember from the last video, everything that red does happens before everything that blue does. Well, in addition to that, blue and red's operations both occur before the game runs collision detection. So if you input and fuse in the same turn, your atom will fuse into the molecule that is input, and you'll somehow be holding the molecule mainly because you never opened up your Waldo. In addition, if you split and output in the same turn, either the molecule or the atom will output. If you're holding the molecule, or if it is not fully within the output zone, the split atom will be output. However, if your molecule is dropped and within the output zone, it will be the first one to go. By the way, if there are multiple eligible molecules or atoms for output, the Waldo will remain on the output symbol and output everything, 1 cycle per item. If blue outputs the remaining nickel here, the reactor would crash. Luckily, since red has a higher priority, I can pick up the remaining nickel before the output kicks off. Note that this has a nasty side effect of blue wasting a cycle since it thinks it's about to output. We can keep blue from going out of sync by using the flip-flop delay mentioned earlier. We could have also made red rotate nickel for one cycle, but that would have wasted time, and of course, using two syncs would waste symbols. Our final symbol for the day is actually completely useless for running a solution. All the pause command does is pause the simulation. This is an excellent tool for debugging. You can hit 4 and go full speed, and you're immediately where you want to be. Well, I guess that wraps it up this time. Round 1 is here, folks. Good luck.